Welcome back. Groundhog Day. So Miguel Martín will continue talking today about, all operators that yesterday weren't able to attain the norm will attain it today, so far as I understood.
Okay, thank you. So let's continue with this series of talk, and I just I just recall the roadmap of the two talk, and we already passed these 3 items. And my idea today is to give these 2, property A and the residuality of not attaining things, and I will speak on finite rank operator. Okay, so the notation, which is very classical, but just to repeat and to fix for the good talk. Let's go to property A and residuality of not attaining things. I just finished my talk yesterday with some open problem, and I say some of them I will try to solve. And one of them was to try to write property A in a way with this isometric, in the mean that let's try to write, it is possible, property A in a way that doesn't use operator, only using properties of the space or properties of the dual at most, or by dual, if we are not lucky. But in the sense of isomorphism, if you ask that every known has every equivalent known has property A, this is the Radon-Nikodym property. But we don't know if there is a isometric counterexample norm by norm. And this is my idea. My idea is to improve Lindenstraut and Bourgain necessary condition for property A, and we don't know if this necessary condition is sufficient, but to check when is sufficient. This is more or less the idea of this part. Okay. So this section is based on this paper with Minggu Jung and Abraham Rueda-Zoca. It was published last year in Journal of Functional Analysis. Let's go to definition, what's it related to RMP. Yesterday I speak about RMP in terms of the diameter of slices. But the Radon-Nikodym property can also be characterized using strong exposition. Okay, what is a strong exposition? Well, you have a subset with this bounded. We don't need closed, we don't need convex, we don't need anything, just bound. And you have a point in C is called strongly exposed if there is a functional such that whenever you have a sequence on the set such that the real part of this functional on this sequence is going to the supremum, then the sequence is going to this point. So you get a functional X star which not only attain the norm on C, the norm in the sense of the supremum of the values, but is attained strongly. It's the strongly unique maximum. Okay, this is equivalent to say that the slices of C defined by the same X star contain X0 and are arbitrarily small. Okay, we will say that this functional is strongly exposed the set C at X0. And we will write a strongly exposed point and a strongly exposing functional. Okay. This is always a G delta subset that can be then or not, but it's always G delta. And let me just, with this picture, to show that this point here is strongly exposed because it belongs to slices, but not any kind of slice. A slice is given by the same functional. This is important to be strongly exposed. The other definition, if you can change the slice, is denting point. But this point here, A, clearly is not even a string, so not strongly exposed. And this point here, B, is a string, but not strongly exposed, because the unique functional attaining is known on B is this one, which is parallel to this line here. So the size of the slices is always bigger than some quantity. Okay, the most interesting case for us will be that the set C is the unit ball. In this case, you have this SE of the ball. If it is dense, then it is the set of non-attaining functional is residual. Residual means that the complement, in a bare space, residual means that the complement is first category. And what is good for residual set? That if you have two residual sets and you make the intersection, you get a dense set, because it's again G delta and dense. Okay, well, here is you have another possibility to see what is a strongly exposing functional on the unit ball is just by the Smulian test, a functional whether the dual norm is FECHA differentiable. Okay. So what are the Lindenstraut and Bourgain necessary conditions for property A? Well, Lindenstraut was only working with the unit ball, working with the usual norm of operator. And he proved that if you have a Banach space with, let's say, separable, if you think in this talk that everyone is separable, there is no problem. Because then every hypothesis like admit a locally uniformly rotan renorming is satisfied, but it's enough. When you have a Banach space admitting a locally uniformly rotan renorming, separable for instance, and has property A, then it's not only true that the unit ball has a strongly exposed point, but the unit ball is the closed convex hull of the strongly exposed point. And Bourgain get much less, just get that the set is dentable, but for arbitrary bounded, closed, and convex subset separable. He needs separability for his argument. But the definition is not property A, but let's say property A for the set C, that the set of operators from X to Y for every Y attaining the supremum on C is dense. Okay, so which is our result? First is applied to every set, not necessarily to the unit ball. Every set, we don't need the set to be convex, we don't need the set to be closed, just bounded. And with the Bischoff property defined by Bourgain, so that the set of operators from X to Y that attain the supremum on C for every Y is dense. And then we get that the set of a strongly exposing functional on C is then in X star. And very in particular, this implies that C is a closed convex hull of the strongly exposed point of C. There is an errata here, it's not BXC. Okay? In particular, if X is, say, separable and has property A, then the set of strongly exposing functional on the unit ball is then in the dual. So in particular, the set of non-attaining functional is residual. Okay, so let's prove this, just this particular case. It is not complicated at all. Okay, the K lemma here is the following. It is the same lemma that Lindenstraut used from the very beginning. If you have an operator with this monomorphism, attain the norm, and the image is a strongly exposed point, which is less than what I wrote here, then the point is strongly exposed. But you get more. It's not only strongly exposed. You can know which are the functional with the strongly exposed this point. And the functional is strongly exposed in this point is S star of Y star for every Y star such that, I write here, Y star X of X0 is the norm of S. This is the same to saying that S star attain the norm of Y star. And this functional attain the norm on X0. Okay, so let's get the proof. Consider a locally uniformly rotan equivalent norm on X, and let Y be this locally uniformly rotan renorming of X plus 2 the base field. This is also locally uniformly rotan, and define this operator Tn, fix X star, and define Tn to be 1 divided by n X, X star of X. These are clearly monomorphism, and they converge to the operator S, which is given by 0 in the first coordinate and X star of X in the second one. In none, there's no problem with that. Now you can find, you know that your space has property A. Then you can find a sequence of operators which attain the norm and are close to each Tn. But Tn are monomorphism, and the set of monomorphism is open. So you can suppose that your operators that attain the norm are also monomorphism. And this is the key, because you have monomorphism attaining the norm. Then, by the lemma, there are element Yn star, which are of this form, such that Sn star of Yn star is strongly exposing, and the norm of Sn star of Yn star is the norm of Sn equal 1. Okay? And now, you may suppose that lambda n goes to lambda 0, just taking a subsequent, and then with an obvious triangle inequality, you get that this lambda 0 x star minus this Sn star of Yn star is going to 0. So lambda 0 x star belong to the closure of this set. But lambda 0 is non-zero. And then you get that x star with this lambda 0 minus 1 of lambda 0 x star is in the closure of this set, and you are done. Let me say that if you are not in the unit ball and C is arbitrary, and you are in the complex case, then you have to work hard, because the set of strongly disposing functional on an arbitrary set, it is, I mean, it is the unit ball, then you can multiply by any number and you are inside. But if you are not in the real case and you are not in the unit ball, the set is not symmetric. You only can multiply by positive element. So you have to prove that x0 is positive. And this is hard. Not very hard, but this is rather hard. But in the case of the unit ball, the proof is very easy. Okay, so let me show an interesting example using these ideas. Well, take the Lipschitz free space on the Euclidean unit circle. Well, we know that this set, the set of a strongly disposing functional, is not dense in the dual. We did the set of Lipschitz function from the unit circle to R. And this was proved in a paper by Chiclana, García-Lirola, and Rueda-Zucca. Hence, by the new result, this space failed in the Strauss property A. This is separable. There is no problem with that. So it has a meta locally uniformly rotan. But actually, we know that the unit ball of this space is the closed convex hull of the strongly disposed point of the unit ball. So by Lindenstrauss or by Bourgain, you cannot prove that this space failed property A. You need this improvement. Let me say that it is not, I mean, I don't know, surely it's possible to find, but I do not know an explicit reference of a Banach space such that the unit ball is the closed convex hull of the strongly disposed point, but the dual is not the closure of the strongly disposing functional. I don't know. I do not know. I know that, but I do not know. Well, let me say that this answers a question of Tony Prochaska that he asked during the defense of the PhD thesis of Rafa Chiclana. The only, in my opinion, the only good thing of the pandemic was that the PhD defense were online, so many people from outside can attend the PhD defense and make interesting questions in this case. Okay, so let me try to go back to pass from this necessary condition, let's say for property A, forget a set by now, that strongly disposing functions are dense, and try to get that non-attaining operators are dense from here. Okay, let me first recall what Bourgain did. Bourgain not only proved that the RMP implies property A, but it proved that if you have the RMP, absolutely strongly disposing operators are dense. What an absolutely strongly disposing operator is the definition of a strongly disposing functional, but as you have an operator, then you have to have, it is clear that it is impossible to have a unique maximum because you can rotate the point. But this is the only possibility. That up to rotation, you have a strong maximum. Okay, but this set is, as a strongly disposing functional, is a G delta set. So if this is dense, then the set of operator, non-attaining operator, is residual. And again, the good thing of residuality is that you can make intersection, countable intersection of residual set, and you get a residual set, so you get density of countable intersection. This is the main point. Okay, so Bourgain proved that the RMP implies that the absolutely strongly disposing operators are dense, and it's much more that the Bourgain-Stigall variational principle that you can do with, you can approximate with a rank 1 perturbation any bounded and upper semi-continuous function. So it is really, really, really general and really usable. Okay, so some comment and question. First observation, all known sufficient conditions for property A, not only the RMP, all actually imply that absolutely strongly disposing operators are dense. So the RMP, property alpha and quasi-alpha that I didn't introduce, that the unit ball is the closed convex hull of a set of uniformly strongly disposed points. So they are strongly disposed. The point of phi are strongly disposed uniformly. So if you have a definition by epsilon delta, it's the same epsilon delta. This is nothing more. And the key lemma is that it is very easy to prove that if you have an operator which attains the norm at a strongly exposed point, then automatically it can be approximated by a absolutely strongly exposing operator. And this is just the idea there. Well, open problem, still open. Does the property A of X imply that the set of absolutely strongly exposing operator is then for every Y? We don't know. We just know that the sufficient condition give that, but in general, we don't know. We know in the separable case, we know for functional, but this is what we know. One easy observation, if the set of strongly exposing operator from X to Y is then for some Y, non-zero of course, then automatically the set of strongly exposing functional is dense. So the question is, can we reverse? We don't know. But at least we can try to ask this less ambiguous question. If the set of strongly exposing functional is dense, for which Y the set of absolutely strongly exposing operator from X to Y are dense? This is what I'm trying to explain here. Okay, but first let me give you example of when the strongly exposing functional is dense to see whether this can be interesting or not. Well, this is true if X has the RMP and then everything is done. If X has property A and admit a locally uniformly renorming, as we prove, if X is locally uniformly rotan, but actually it is enough that the set of every point in the unit sphere is strongly exposing. This is enough. And this is called A-LUR, almost locally uniformly rotan. And for instance, this is also true for the dual of the James 3 space. And in these three cases, we do not know if this space has property A or not. We don't know. Okay, so the objective is to find spaces Y. More interesting if we don't know if these spaces Y have or not property B, so that the set of absolutely strongly absolutely strongly exposing operator from X to Y are dense whenever the strongly exposing functional on X are dense. Okay, so a first family of example. This very general result. Suppose you have an ideal of operator, but you can think about the compact operator or the set of all operators. This is enough. Suppose you have an ideal of operator which contain rank 1 operator. Suppose that the set of a strongly exposing functional is dense. And the hypothesis from Y, or well, he now is on X and Y. There is a sequence on the unit sphere of Y star such that the set of operators such that the adjoint attain the norm in one of the elements of the sequence is residual. So dense and contain a G delta dense. Then the set of strongly exposing operator from X to Y which belong to the ideal is then in the ideal. And the idea of the proof is rather easy. Consider the set B of those operators such that T star of Yn star is strongly exposing. This is residual. Why? Because fix 1n. It is very easy to prove that this is residual. Why? Because it is residual contain the countable intersection of open dense set. And for an open dense set, this is just open mapping theorem. And then you make the intersection, countable intersection for 1n. And now make the intersection on all n. But countable intersection of countable intersection is countable intersection and you get residuality. Okay, good. Lemma. Suppose you have an operator and that the adjoint attain the norm in such a way that the image of the functional at which it attain the norm is strongly exposing. Then, well, we can forget this, T is in the closure of the absolutely strongly exposing functional. Okay. Then what we get is that this E intersecting with this B, the intersection of two residual is residual. And this lemma gives you that this is contained here. Is it clear? Because what you are saying is that I'm taking here all operators that all this image are strongly exposing. And here, are operators at that the adjoint attain the norm at one of these points. So the intersection satisfies this, and then it's in this closure. Okay? Okay. So first consequence. Suppose that the set of strongly exposing functional is dense of X on X, and Y star has the Radon-Nikodym property, and the set of strongly exposing functional on the unit ball of Y star is countable up to rotation. Then the set of absolutely strongly exposing operator from X to Y is dense, and the set of absolutely strongly exposing compact operator is dense in the set of the compact operator. Okay, you can apply this to a Y being a pre-dual of little L1. We don't know if this has property A or not, property B or not, but this is very interesting. Y finite dimensional such that the set of strongly string point of the dual is countable. But I told you yesterday that the only finite dimensional spaces known to have property B are either those with the dual has finitely many string point, this polyhedral, or another property with this called property quasi-beta that gives you some discreteness of the string point of the dual. But this can be very non-discrete, just countable. So it may have the Gould sphere as a accumulation point, so there's no problem with that. Okay. So the second consequence is that you get suppose Y has the RMP, suppose Y has the RMP, and the set of strongly exposing element of the unit ball is countable after rotation. Then you get the same, but arriving to Y star. And this, for instance, applies to the Y of the Lichy free space of M. So Y star is the space of Lichy function on N when N is countable and proper. Proper means that the that closed unit ball are compact, isn't it? Yes. Okay. So second family, third consequence, and third family of example. Suppose you have a Banach space Y such that every separable subspace of Y admits a countable Jens boundary. Then compact operator without absolutely strongly exposing are dense. And this applies to any polyhedral. I put real because polyhedrality is usually defined in terms of real, only for real spaces, but there is an easy extension to the complex case anyway. But also, when Y is a closed space of CK, when K is Haldor and scattered. So this is CK is asprum. And no separability condition is needed. You can go down to separable subspace to get the result. No problem. Okay, second family of new example. Well, now instead of having countably many strongly exposed points, the hypothesis is that the set of strongly exposed point of the unit ball of Y has the RMP, but the set of strongly exposed point is discrete after rotation. So you have a sequence of a strongly exposed point which converges to a strongly exposed point, then it has to be after rotation, constant, almost constant. Then the set of absolutely strongly exposing operator from X to Y star is dense, and if you intersect with any ideal, then you get the same. Well, just a brief idea of the proof. The idea is, but this is an idea that is very nice, that if you go from X to Y star, then this is absolutely the same that going from Y to X star. These two spaces are isometric, just taking the adjoint and restrict the adjoint to X. There's nothing magical here. Then we use Bourgain ideas, the discreteness hypothesis, the residuality of the set of strongly exposing functional, and then we get operator from Y to X star, and non one element such that T attain the norm at Y, and Ty is a strongly exposing functional. But just take the pre-adjoint and restrict to X or whatever. you want, I mean, the isometry here, and what you get is an operator which said that the adjoint attain the norm, and the image of the functional where it attains the norm is a strongly espousing functional. And this gives you that this operator is in this closure. Okay, so this can be applied when a strongly espousing functional is dense, and Y has the RMP, and the strongly espousing point, strongly espoused point of BA or BY is discrete to rotation. Then you get this for operator or for compact operator, and this can be applied, for instance, to we will arrive to Y star. So Y star is the set of Lipschitz function on M when N is a discrete metric space. Let me finish with some related open problem. Well, the first problem is, does this necessary condition that we did for operator for Banach spaces and meeting a locally uniformly rotan is true for every Banach space? So we can remove the locally uniformly rotan condition? We don't know. But the point is that if yes, then you apply this to L infinity, and you get that L infinity fail property A, because L infinity has no strongly espoused point. So you're done. And then I asked yesterday whether every dual space has property A. That this is something we don't know. And then this will be a contact sample. Okay, we don't know. But if the answer is no, then for big spaces, the property A behaves different than for separable one. Which looks to be complicated, but I don't know. Because if your space doesn't admit a locally uniformly rotan equivalent norm, then it's very hard to use the norm attainment in the way we are using. We don't know. Maybe you can do in another way, but we don't know. The second problem is that we don't know in general that if the denseness of the strongly espousing functional implies that the set of absolutely strongly espousing operator is then for every Y, or at least that the set of non-attaining operator from X to Y is then for every Y. We don't know. And the third open problem is just try to find condition on Y to get that the set of strongly espousing operator from X to Y is dense whenever the set of strongly espousing functional is dense. Let's say Y finite dimensional. We don't know. It's hard to believe that the answer is no, but we don't know. Or Asplund, or the dual of an RMP. These are the possibilities. So more or less what I am saying is that can we remove the countably or discreteness hypothesis in the theorem I presented before? We don't know. Okay, so let's go to finite rank operator, and this will be the last part of my series of talk. And this is the, I think I put yesterday that this is the problem whether finite rank operator can be always approximated by non-attaining operator is in the word of Johnson and Wolfe, the most irritating problem that this is still open in the field of non-attaining operator. Okay, first we will see some classical sufficient condition, some new sufficient condition, and if we are trying to find a contract sample, that is more or less our idea, then I think more or less I explained yesterday, our idea is to try to find a Banach space X such that every non-attaining operator from X to a two-dimensional Hilbert space is of rank 1. If this is 6, then this gives that the two-dimensional Hilbert space has not property B. We don't know, but I will try to show you how to construct rank 2 operator and where you can go using these ideas. Okay, so let's start with the the main part of this section is based on this chapter by Vladimir Kader, Ginés López, and Dirk Werner and me on non-attaining operator of finite rank, which was published in the book of the mathematical legacy of Victor Lomonosov. Okay, so some preliminaries. Recall that not every compact operator can be approximated by non-attaining operator. So finite rank has to be used. It's not compactness, it's something more. Okay. So the problem is, can finite rank operator be always approached by non-attaining finite rank ones? So if we look for properties allowing to approximate compact operator by not attaining finite rank operator, then we need some kind of approximation property. But it was the classical approach of the 70s. The paper from the 70s tried to see that compact operator attaining the norm are dense, proving that compact operator can be always approximated by finite rank non-attaining operator. So you need some kind of approximation property. And what they did is that use strong approximation properties to get this result. Okay. So the new ideas, if you want only to deal with the finite rank operator, you have to forget completely about approximation property. And this is our idea. But instead of approximation property, we will use some kind of linearity in the set of non-attaining functional. I will show. Okay. So first, before going to the classical result of the 70s, some obvious observation. First, just the notation, finite rank non-attaining operator. So self-explained notation. Well, if you have property A, then automatically, what means property A? That operator from X to Y can be approximated by non-attaining operator. If your operator, your starting operator is compact, you cannot assure that the approximating operator are compact. You don't know from the definition. But if your operator is finite rank, just take the rank as a target space, and then you approximate, and then you see the operator going to Y. And then what is true is that you have property A, then finite rank non-attaining operator, the closer of this contain finite rank operator. Okay, so the RMP, alpha, quasi-alpha, every separable Banach space can be renowned to have this property. Well, it's not interesting. But there is an open problem. What is not clear is that imagine you have Y with property B, of course not finite dimensional Y. It is true that in this case, finite rank operator can be approximated by not attaining finite rank operator. This is not clear at all, because you cannot change the target. Because if you change the target, what you have is a subspace of Y. And it is not true that when Y has property B, every subspace of Y has property B. L infinity has property B. And every separable Banach space is subspace of Y. So, no way. Okay. So the classical results are the following. Let me go here. So Johnson and Ward prove if you have the approximation property in this very strong way, that you have a net of finite rank non-one projection such that the adjoint converges to the identity in the strong operator topology, then for every Y, compact operator can be approximated by finite rank non-attaining ones. And the idea is very easy, is that if T is compact, then TP alpha goes to T, and TP alpha attains the norm because P alpha is finite dimensional, and the unit ball of P alpha is the same that P alpha the unit ball. So here you have that there is an element attaining so that this operator attains the norm, but this element should came from an element of the unit ball. So this is rather easy. I will explain something stronger than this, so we can skip this. And this applies to CK, C0L, L1, pre-dual of little L1, and subspaces of C0 with monotone Schauder basis. But we know that there is a subspace of C0 with Schauder basis and a compact operator from it, which cannot be approximated by non-attaining operator. So the word monotone is very important. The K point is 2. The basis constant up to 2. But we need monotone in any case. But and this, as I think I said yesterday, this space has a Schauder basis, but the basis constant is 8. And it cannot be less than 2. Okay. For rank space, well, if for every finite dimensional subspace of Y, you can find a polyhedral finite dimensional subspace of Y which contain it, then, and you have the approximation property, then the compact operator from X to Y is the closer of finite rank non-attaining operator. If you delete this part, the same argument gives you that finite rank operator going to Y can be approximated by finite rank non-rotating operator. And this applies to pre-dual of capital L1 or for L1, but in the real case, or for any polyhedral with their approximation property. Okay, so let's go to the new condition. The new condition is forget about approximation property, but think on linearity of the set of non-attaining functions. And the big theorem, I mean, the main result is the following. Suppose that you have a Banach space such that given finitely many functional and one epsilon, you can find finitely many functional, each of these is close to the previous ones, and so that the linear span of the set of the new functional is contained in the set of non-rotating functional. Then every finite rank operator can be approximated by finite rank non-rotating operator. The easiest way to get this is suppose that the set of non-rotating functional is a linear space, like in C0. Then as this set has to be dense, it's a linear dense subspace, and then you get this for free. Okay. And we don't know any example whether you have this and not the other. But, well, idea of the proof. Take the finite rank operator, and you can write as a finite sum of functional tensor vector. Take this Ci of the hypothesis and consider S chain Xi star by Ci star. Of course, this is S is close to T, but what is the adjoint of Y star is the image of the adjoint of S is the annihilator of the kernel of S. But this is contained here, clearly, and this is contained here. And you use the following lemma that will be very important. Suppose you have an operator from X to Y, and suppose you have this, the adjoint of the operator attain the norm as some Y star, and the image of by T star of this Y star is a non-attaining functional. Then T attain the norm. This is immediate, but let me just write. If T star of Y star belong to NA XK, then there is X0 in the unit sphere such that the norm, modulus T star Y star on X0 is equal the norm of T star Y star with what the norm of T. But this is modulus Y star T X0, and this has to be less or equal than the norm of T X0. So at the very end, I get that T of X0 has norm bigger or equal than the norm of T, so T attain the norm. Okay, and this is why, by this lemma, this S is a non-attaining functional. Okay, so where you can apply this result? All cases covered by Johnson and Wolf result. CK, L1, pre-dual of little L1, all of this. Or when the set of non-attaining functional is a linear subspace, as I said. For instance, this is true for compact operators from L2 to L2, or X being a C0 sum of reflexive space. So you are very far of having anything related to the approximation property. You can be very far. Or proximal finite codimensional subspaces of either C0 or K of L2 of L2. Okay. But let me finish the talk trying to show how you can get finite rank non-attaining operator. The idea is to try to show you how a possible contact sample can be produced. But by now, we don't have the contact sample. Okay, so the open problem is that if you have two Banach spaces and of dimension bigger than 2, does there exist a finite rank non-attaining operator from X to Y which has rank 2? We don't know. So if not, we will get a contact sample to the most irritating problem. But let me give you this notation. NA2 are non-attaining operators from X to Y of rank 2. And the problem is whether this can be empty or not. Okay, so the first remark is that let's think a little bit about Y. If Y is not strictly convex, then you can always produce such an operator. Why? Because if Y is not strictly convex, then you have some segment in the unit ball. Yes. And then you can put here, not very well written, copy of L infinity 2, but inside L infinity 2, you can produce always rank 2 operator, no problem. For many reasons, you can do by hand. But for instance, because L infinity 2 has Lindenstrass property B. So they are dense, so they have B. But it's easy to do by hand. And then the operator you get here, touch here, and has rank 2. So it's also a non-attaining operator when I rise to Y. But this is rather easy. Okay. The second remark is that if you are able, you pick X, and you are able to produce a rank 2 operator arriving to L2, or to L2, which is the same, then you get non-attaining, rank 2 non-attaining operator from S to Y for every Y. At the moment, the dimension of Y is bigger than 2. And this is just the transitivity of L2, the norm of L2. Is it clear? Okay. No, let me show. Okay, so you go from X to L2, and this is S with this not attaining, and now go from L2 to Y, any T, and the only thing is T is injective. The only important thing. Okay, this T has to attain the norm. Has to attain the norm somewhere. TC is equal, the norm of TC is equal to the norm of T. You know that S of X0 is the norm of X. The problem is, if S of X0 is C, you are done. But you are in a Hilbert space. So up to isometry, you can get that C is exactly S of X0. So the idea is that you may change, you may suppose that T, up to an isometry, you may suppose that C is equal S of X0 up to isometry. So, okay, good. So we can focus on L2. This is the only important part. So the open problem is, does there exist an Banach space X with dimension bigger than 2, so that the set of non-attaining rank 2 operator from X to L2 is empty? If yes, then non-attaining operator from X to L2 will be not things. So, good. Okay, sufficient condition to get that this is non-empty. First one, suppose this is the one we use, Johnson and Wolfe use. Suppose you have a projection with rank 2 and non-1. You need non-1 and projection to get this. Then you are done. Just factor through the projection. This is no problem at all. You go from X to PX, and from X, so from PX with this dimension 2 to L2 using an operator with this bijective. And then you are done because of this condition here. Okay, so good. But there are Banach spaces for which every non-1 projection is either of rank 1 or the identity. Even finite dimensional, which is rather hard to believe, but it's true. I don't know if this is the first example, but this is the first example I was able to find. Okay, but if you think a little bit about this result, you are not using that P is a projection at all. What you are using is this condition, PBX equal B of PX. Then why, instead of using projection, using quotient with the same idea? But you need this in the quotient. So for quotient, you can do the following. Suppose you have C is a subspace of X of codimension 2. And text X goes to X over C. Now goes from here to L to 2 with T with this bijective. And consider this T tilde here. And this is the quotient map. Again, this has to attain the norm because this is dimension 2, and this operator has rank 2. But what you need that T. And for this, what you need is that the element where this T attains the norm here is the image by Q of a non-1 operator, or non-1 element. So what you need is Q Bx equal Bx over C. And this is exactly the definition of proximality. So if you have a proximal subspace of codimension 2, then you are done using this idea. Okay, good. No good. Shall read proof that there are Banach spaces which contain no finite codimensional proximal subspaces of codimension bigger than 2. So, no hope. Okay, let me go further. When you make this proof, you use proximality to get easily that this T tilde attain the norm. But this is the same lemma I wrote several times. If you have an operator such that the adjoint attain the norm and the image where the adjoint attain the norm is a non-attaining functional, then you are done. So imagine, I don't know whether, no, sorry. Imagine you have a subspace of two-dimensional subspace instead of the non-attaining functional. Then, instead of it's correct here, take an operator of rank 2, anyone that has to attain the norm, write S as S tilde with with the quotient map, and then S is rank 2, and the adjoint attain the norm, of course, as the image of the adjoint is the Gould image is contained in the set of non-attaining functional, then using the lemma, you get that this S attain the norm, and you are done. Okay. But Remutil prove that the read space satisfies that the set of non-attaining functional contain no two-dimensional subspaces. Problem. How to work? Okay. What can do next? Well, the last finite condition. First, read space and other construction of the same kind of norm are not smooth. But if the Banach space is not smooth, this means that there is a point at two functional which attain the norm at the same point. But then it is obvious that this operator is rank 2 because they are linearly independent and attain the norm. So, okay, but more problem. You can renorm read space with the same property that the set of non-attaining functional contain no subspaces and is smooth. So you cannot use this in this new read space with this smooth. Okay? So there are a posteriori read spaces that are smooth. I mean a posteriori because you make them smooth after you produce that they are read. Okay, so what we do now? Well, in any case, as the set of non-attaining functional is the same, maybe it is smooth, so this means that the unit sphere of the dual intersecting with the non-attaining functional contain no segment, but what surely contain is cones. Okay, so what happened with cones? That is a Banach space satisfied that the set of non-attaining functional contain non-trivial cones, then there is a non-attaining operator from X to L to 2 of rank 2. Okay? So, sorry. Shall I take 5 minutes? Okay. So we prove in a very complicated way in the paper, but there is a simpler proof using ideas I discussed with Cabello brothers. Just the idea is that for any two-dimensional space, the element in the unit sphere are with a non-degenerate ellipsoid contained in the unit ball, thus the unit sphere are then in the unit sphere. This is the idea by Cabello and Cabello. They say obvious in the paper, but then I call Félix, and he explained me, and they say, this is true, it's obvious. Okay, as these contain non-trivial cones, you can find a two-dimensional subspace for which the set of non-attaining functional intersecting with the unit sphere has non-empty interior. Then you may find a non-degenerate ellipsoid contained here, touching the unit sphere at an element of here. But then you are done. Because just the ellipsoid define an injective operator which attain the known, and the image of the point where you attain the known is a non-attaining functional. Okay, just go take that joint or pre-adjoint or whatever you want, and you are done. Okay, open problem. To get a possible counterexample, we have to eliminate cones from non-attaining functional. But is real non-attaining an open problem? No. The ultimate example. I just uploaded today to archive the following result. There exists a Banach space X such that the set of non-attaining functional contains no cones. Actually, it is the worst possibility you can imagine. Taking two linearly independent non-attaining functional on this space, no other point of the segment between them is non-attaining. So this is a possible counterexample because we have no idea how to produce a non-attaining operator from here to L22. And just that the proof, well, you can forget a little bit this explanation of how to prove this because it's just taking the construction we did in this paper and produce not a posteriori smooth, but a priori smooth. But to get a priori smooth, we had to use known on L1, which are smooth, but behave like the known of S1, L1, asymptotically. Let's say asymptotically. Sorry. Okay, so just let me finish with some open problem. The main one is whether every finite dimensional Banach space satisfies linear zero property B, or for L22, that we don't know, or even whether this set can be empty for some X, or why not try to prove for this space, because this is the candidate we have. By now, we don't have any other candidate to be a counterexample. Okay, so, oh, sorry, there are more. Well, the problem is find condition on X, and to assure that that finite rank operator can be approximated by finite rank non-attaining operator, and a possible idea can be, okay, using the ideas of Cabello and Cabello, you can try to work a little bit. But the problem is, imagine you have the set of non-attaining functional is residual. Then if you intersect with another residual set, well, you are happy because what you get is dense. But the problem is that the set of inner point, even in the two-dimensional space, can be not residual. It's always dense, but it can be not residual. It can be of first category, isn't it? So, no way. We don't know anyway. Okay, so that's all, folks. Thank you very much for your attention.
Good. Questions, remarks, or comments, or anything?
Miguel, hay una noción en el libro de Banach de operadores lineales que no se utiliza, no la utilizamos, yo sí la he utilizado, pero no es habitual, que es la de F norma. tiene todas las propiedades de la norma, pero Banach lo llama F norma porque la desigualdad triangular no es tal, sino con una constante. Es la única diferencia.
Casi norma la llamamos también, ¿no?
Entonces son cuasi Banach, en fin. Pero la noción de F norma, lo que sí sabemos es que los espacios con la RNP tienen una F norma LUR. Entonces mi conjetura, después de oír tu charla, es que la noción de F norma va a ayudar porque saldrán gratis todas las cosas que tienes de la RNP. Porque los espacios con la RNP van a tener una F norma de ese tipo. Y en todo caso va a depender de algo que le gusta mucho también aquí a la gente presente, que es la teoría de conjuntos. Es decir, puede ser que al final todo dependa de asumir o no asumir axiomática. Pero lo primero, desde luego, es una F norma, Stephen Banach, Book, Linear Operators, y ver si una F norma LUR produce lo que tú quieres, que probablemente sí.
No lo sé. Gracias, pero no lo sé. Lo miraré. So thank you. I will think of.
Okay. Pepe, please, what is the notion of F norm you are referring to?
Quasi-norm.
Quasi-norm?
That the quasi-norm of x plus y is more or less that the constant norm of x plus norm of y.
But this should be homogeneous?
I don't know.
Because the space of all random variables, for instance, has an F norm, but has no continuous operators into any locally bounded space. So the notion of F norm is very delicate in this context for norm attaining things, I think. I suppose that you need at least homogeneity and maybe more than this.
Homogeneity is something you are using always, because it's something you have, so you never are thinking of, but you are using always.
But in any case, in LP with capital LP with P below 1, smaller than 1, you have no operators into any Banach space nor into the ground field. So
I don't know.
So the point is, what are you meaning by an F norm in a Banach space?
I'm very sorry because I just looking at you, just I said in Spanish. Sorry. The only thing that I wanted to explain is that there is a notion in the book of Banach, linear operators, which is the one of F norm. And it's possible to work with F norm with the LUR property. And all known RMP spaces has this property, all of them. So the conjecture is that looking for the property of density that you are studying, when you ask LUR, ask only F LUR, and then you have inside all RMP spaces, and probably it will be true. Okay? So, sorry, I just telling you in Spanish. Thank you.
Good. Has anybody the book of Banach over here? Okay, then let's thank the speaker again. A couple of minutes and we'll be back. It's funny that after so many years of friendship, this is probably the first time I have the chance to introduce Professor Manuel González, who will talk to us about the properties of Rochber spaces.
Thank you. Well, first, I'm grateful to the organizers of the meeting for giving me the opportunity to give this talk. I'm going to describe some results that are joint work with Jesus Castillo and Raúl Pino from the University of Extremadura. And our work was supported by the Spanish government. Well, these spaces that we call Rockwell spaces were initially studied by Rockwell and other people as a kind of higher order interpolation spaces. However, Rockwell considered only finite dimensional spaces, so from our point of view, that results were trivial because we are interested in isomorphic properties of Banach spaces. Here is the introduction. There are several ways to introduce these spaces, and I have chosen the shortest one. I consider that as a part of complex interpolation theory. So I consider a concrete interpolation pair formed by little L1 and C0, and we consider the associated Calderon space, that is a space of analytic functions on the unit strip with values in C0, and for these functions the evaluation of the derivative at any point of the interior of the unit strip is continuous, in particular in the point 1/2. And then this is the definition of the Rockwell space. This is a space of n tuples of vectors of C0 and given by this expression. We can see this space as a quotient of the Calderon space, the quotient between that space and the intersection of the kernels of the evaluations of the derivatives. And in this sense, this is a Banach space. However, the norm that produced this definition is not good in practice. It is usually not good for calculations. Usually we have to use not a norm but a quasi-norm in some sense. I begin with some basis information. If we consider the evaluations of the functions in the points 1/p with p in the Calderon space, this gives us the LP space for 1 less than p less than infinite. So, in particular, what we call R1 is the space little l2. Then in the second space is the Calton space that can be considered as a twisted sum of two copies of L2. Well, here we consider an exact sequence in which I is an isomorphism, P is a surjective operator, and the image of I is equal to the kernel of P. This is a notion of exact sequence. Well, in this case of exact sequence, we have some trivial cases in which the kernel of the surjective mass is complemented. So in this case, the intermediate space is isomorphic to the product of the spring spaces. But this doesn't happen in this case because here the injection is a strictly singular operator and the surjective map is strictly singular. So it's a highly non-trivial exact sequence. Well, then the properties of zeta 2 are in some sense non-trivial because this is a space that is saturated by copies of LP, however, it does not contain complementing copies of LP. And then the space Rn can be seen as the twisted sum of n copies of L2, because we have another exact sequence like that, then inductively we see that this space can be obtained summing n copies of little L2. Well, as before, this exact sequence is non-trivial because the injection is strictly cosingular and the surjective operator is strictly singular. With respect to those spaces, the Rockwell spaces, I have to say that I think they are very interesting spaces because in some aspects the properties of Rn are similar to those of little L2. But in some other aspects, they are very different spaces. We will see several examples in the talk. Well, I'm going to begin with a property that is related with an open problem, and there is a fact that the space of Carlton-Peck zeta 2 is isomorphic to its subspaces of codimension 2. And this is very easy from the definition. However, it is not known if this space is isomorphic to the subspaces of codimension 1. In fact, this space was constructed previously, before the hereditarily indecomposable spaces were constructed. These are examples of spaces that are not isomorphic to the hyperplanes. Then, at that moment, when the zeta 2 space was constructed, some people expected that could be a counterexample to the hyperplane problem, a space who is not isomorphic to the hyperplanes. And, well, people tried to solve the problem, but it remains open. And the problem is that, as we described before, the space zeta 2 is in a space of pairs. Then, if you consider the pairs, if you consider the space as a sequence of pairs, it has an unconditional behavior, and it's very easy to work with them. But if you consider the norm acting on the elements of the pair, it has a nonlinear component that is not easy to work with. So in particular, if you consider, well, this space has a basis. If you consider just the translation of the basis, it's not possible to know if this operator is continuous or not. Then, at this moment, it is not known how many complemented subspaces it is not known how many complemented subspaces has this space. It's possible that it has only one, the whole space, and it would be a new example of a prime space. Maybe it has only two, I mean the whole space and the hyperplanes. and maybe there are more. And something similar happens for the Rn spaces, the Röhler spaces of order n. In this case, the space is easy to see that is isomorphic to their subspaces of codimension n, but for k less than n is not known if the space is isomorphic to these subspaces. So we have similar possibilities. Maybe they are prime spaces, or maybe even it has only n complemented subspaces, but it would be a very special space, or maybe there are more complemented subspaces. Well, next I describe a relatively old result about the structure and the relation between the Röhler spaces. The idea is that the Röhler spaces of higher order are twisted sums of the Röhler spaces of lower order. Concretely, if you consider if we consider two integers, then we can embed the space of order k, that is formed by couples, in the space of order k plus n using this map. Just this map defines an into isomorphism, and also this map from R sub k plus n into Rn defines a surjective map, so that the image of the embedding is equal to the kernel of the quotient map. So you obtain an exact sequence, and the space of order k plus n is a twisted sum of Rk and Rn. This sequence is non-trivial because another time the embedding is strictly cosingular and the surjective operator is strictly singular. Another property in which the Röhler spaces are similar to the Hilbert space is that these spaces are isomorphic to their dual space. This was shown for the case of the Carlton-Peck space by Carlton and Peck, and for the case M bigger than 2 by Cabello, Castillo, and Correa. In fact, the isomorphism between the space and the dual space is very simple in terms of the representation of Rn by means of n tuples, and is just given by this expression. This has very interesting consequences because, well, if we consider an operator in Rn, we have the conjugate operator acting in the dual space, but using the isomorphism between Rn and its dual, we can construct an adjoint operator, given by this expression. That is, like it has similar properties to the conjugate operator because the n is an isomorphism, but it acts in the same space. So we can consider, for example, expressions in which appear the product of the adjoint and the operator. That this is what happens in the Hilbert space and what makes the operator theory in Hilbert space very rich. We prove, for example, this technical result in which these two properties are equivalent. Well, if we have an operator between two Banach spaces, the operator is upper semi-threshold if the kernel is finite dimensional and the image is closed, and it's lower semi-threshold if the image is finite codimensional and also on the range is closed. Well, this result we will see later that is useful to prove some results. I think one of the points in the theory of the Rockwell space is the study of operator theory. There are some results and some interesting results, but I think that there is an open field to work on topics. A concrete problem is if we consider the group of invertible operators in Rn, if this is a connected set. The result is true for Hilbert space, for the little LP space, but we don't know what happened in this case. And also try to study the operators using the adjoint. I think this could be useful, and well, we can consider notions similar to self-adjoint, normal operator, and things like that. Well, here we are going to see one of the remarkable properties of these spaces. Well, first, it was proved by Carlton and Peck that the complemented subspaces of zeta2 contain copies of zeta2 that are also complemented in the whole space. And this result was extended by Castillo and other people for the case of the Rn space. Then in our case, we were able to prove a result that is new even for the Carlton-Peck space, and it is the fact that all the copies of Rn in the space Rn are complemented. This is a remarkable property because there are few Banach spaces that have it. For example, Hilbert spaces, and then there are other spaces that have the property because they have some kind of injectivity property. For example, C0, C0 de gamma, or injective spaces like L infinite. But for example, if we consider the space LP or LP for 1 less than infinite, different than 2, then each of these spaces contains a copy of himself that is not complemented. Well, and from that results of the copy of Rn in N, we can obtain a corollary about the properties of operators in Rn that says as follows. Suppose that the image of T is closed and the kernel is finite dimensional. Then the image of the operator is complemented. In this case, not necessarily isomorphic to R2, and if the image of T is complemented, then the kerr of T is complemented. Well, using the notion of upper and lower semi-Fredholm operator I described before, what says this result is that the semi-Fredholm operators have always complemented kernel at range. Well, this is more or less a standard result, and is the fact that the Roggeberg space inherit all the three space properties that have Hilbert space. Because, well, for example, zeta 2 is the twisted sum of two copies of L2, and this exact sequence shows inductively that the Rn spaces is a copy of n, is a twisted copies of n copies of L2. Well, here the notion of the space property is that P is 3 space if given an exact sequence from the fact that the subspace and the quotient have the property, it follows that the space has the property. Hilbert space has many free space property, but for example, I will point that the Roggeberg space have type 2 minus epsilon and cotype 2 plus epsilon for every epsilon bigger than 0, that these spaces are reflexive and hereditarily L2, that every closed space of infinite dimensional contains a copy of L2, and that they are super reflexive. But there are more properties of this kind. Well, now, with respect to the existence of bases and conditional decomposition, it was recently proved that the space zeta n has an unconditional and dimensional decomposition. And as a consequence, one can derive that the space has also a Schauder basis, but this basis cannot be unconditional for n bigger than 1. Then I'm going to describe some results about subsymmetric basis sequence. Recall that a basis sequence is subsymmetric if it is unconditional and it is equivalent to all their subsequences. And here is the result. Then for every k, we consider an Orlich sequence space, LFK, given by this function that is equivalent to an Orlich function. Well, it's very well known that the unit vector basis of this space is symmetric, in particular is subsymmetric, and these spaces satisfy algebraically these inequalities. what is equivalent that the norms satisfy these inequalities. Then the space Rn contains isomorphic copies of the first n of these Orly spaces, and we have an additional result that if we have a normalized weakly null sequence in Rn, then we can find a subsequence that is equivalent to the unit vector basis of Fk for some k in between 1 and n. Then we can see that the spaces become more complicated when k is increasing. And in particular, we can derive from that the space Rm and Rn are not isomorphic for different m and n. About operator ideals, we are going to consider the strictly singular operators and the strictly cosingular operators, and we can show that that the identity of Rn factorized through any non-strictly singular operators. So as a consequence, the strictly singular operators contain any proper ideal in the space. And this is another remarkable property, and is that if you have a strictly singular operator in Rn, then the n power of this operator is compact. However, we can find a strictly singular operator in Rn so that the n-1 power is not compact. This also shows that the Rn are different for different values of n, and is also a remarkable property that is satisfied, for example, for similar version for LP spaces of functions, but more or less the result is that the square of a strictly singular operator is compact. And also the strictly singular operators coincide with the strictly cosingular operators. This is essentially consequence that the Rockwell space is isomorphic to its dual, and also since these spaces are reflexive, the duality between a strictly singular and a strictly cosingular is perfect. And then finishing, we are going to consider symplectic Banach spaces. These are spaces that has some interest in mechanics, but well, usually they consider not symplectic Banach spaces, but symplectic Banach manifolds that are structures more complicated than just a vector space. So a space is symplectic if it contains a continuous alternating bilinear map from x to a times x to r, so that it defines through this formula a bijective isomorphism from x to x star. The trivial example of symplectic space is you take a reflexive space and the product of y and its dual is a symplectic space. Just consider this expression for omega. The idea is that we are going to show that there are non-trivial symplectic spaces. In order to do that, we consider the notion of isotropic subspace, in which the form omega is equal to 0. A subspace is Lagrangian if it is isotropic and it has an isotropic complement that is also Lagrangian. And then it's not difficult to show that one structure of symplectic space is trivial if and only if it contains a Lagrangian subspace. Then Carlton and Swapson were able to show that in the space θ2, every Lagrangian subspace is finite dimensional. So, no, that every complementing isotropic subspace is finite dimensional, so it has no Lagrangian subspace, and the θ2 is a non-trivial symplectic space. Then we are able to show the same result for n bigger than 2. Here the definition is not quite the same. In fact, we have to distinguish the case n even and n odd. In this paper, you can find the contents of my talk, the result I have described. Especially in the last one is a survey paper in which you can have a good description of the result. And in fact, at this moment, we are preparing a more complete description of the spaces. And that is all. Thank you.
Other questions or comments? Remarks? Okay, then.
Thank you. Regarding the fact that the power of a strictly singular operator is compact, was it already done for the square in the case of Carlton-Peck? Do you know that?
Well, in the Carlton-Peck, it works for the space, but our result is new. It wasn't known before.
Okay. Thank you.
Any other question? Okay. Then let's make a 25 minutes break, coffee break, and back again. Thank you. Well, it's again a huge pleasure after so many years of friendship, one of these extraordinarily rare occasions in which I can introduce Félix Cabello, who will talk about something
Ponematics.
weird. Something weird.
Okay. Thank you, Jesus. First of all, I want to thank the organizer for organizing this meeting with so many beloved friends.
Ah, aquí, se ha caído. Tiene que ser aquí, a ver si puede ser aquí la camiseta.
Vengo.
Ay, no, a ver,
¿Ahora?
yo creo que así mejor.
Pero si se oye bien en voz normal. Vale. Well, I haven't had time to write down a decent abstract, so I should explain what are ponematics or ponemaths. This is a joint project with William Correa, and well, ponematics is to ordinary analysis of Banach spaces and infinite dimensional Banach spaces, more or less like ponies are to normal size horses, or babies are to their parents, or well, I think that I can explain it better. The leading idea is that you can extract a lot of information on infinite dimensional objects by studying quasi-normed groups of very low dimension. So the object of study are mainly quasi-normed groups of low dimension. So let me explain what is a quasi-normal group. Okay, we need an abelian group and a quasi-norm, which is a non-negative function which vanishes only at the origin and is even and satisfies our weak form of the triangle inequality, which this should be this if delta was 0, but it's not 0. And then a quasi-normal group is just a group with a quasi-norm. In a quasi-normal group, you have a topology for which the balls that are from sets for a neighborhood basis of the origin. But in a quasi-normal group, you can measure size, and so this is more than a topological group, more or less as a metric space is more than a simple example of topological space, or a Lipschitz function is not only a very nice continuous function. Let me present some very typical and easy examples. The simplest ones are the ground field with the powers. Well, this is a quasi-norm on the ground field for any p. For p less than 1, this is clear because of this is even subadditive by concavity. And the difficult case is when p is greater than 1. And then the constant for the quasi-norm appears in this string of inequalities, which are, all of them are obvious. And then you put the p here and here, so you get that this is a quasi-norm with a certain constant which is greater than. Of course, and still in the one-dimensional case, we can consider all Orleans, but not necessarily convex functions that satisfy the so-called delta 2 condition, which is this condition. And this is necessary to make them a true quasi-norm on the ground field. But, okay, less typical and more interesting are, for instance, any Young function on Euclidean space. Okay, of course, satisfying the delta 2 condition, because if not, you have no quasi-norm. And my favorite one, which is Rife quasi-norm on the plane, which is given by this formula. This log is the non-linear part of the norm in Carlton space Manolo mentioned before. And let me, okay. In the picture you can see some balls of Rive's quasi-norm. You can see that a quasi-norm in the plane is a more complex object than a norm on a two-dimensional space, because in a Banach or Normes space, when you have seen the unit ball, you have seen all balls. But in quasi-Normes space, different balls have different shapes. So, on which ball is the functional to attain the norm? More generally, we can introduce a number of Carlton-Peck type quasinors on the planes, just adding here a Lifshitz function on the line vanishing at the origin. And as an important fact of the pony theory is that if you have a quasinor, then the powers are also quasinor, just in the scalar case. And of course, all these quasinors are standard. That means that they all induce the usual topology of the Euclidean space. Non-standard quasinors are out of reach because the line, the real line, is already a huge group. So, for instance, as a group, it is isomorphic to any vector space where the cardinality is the continuum. For example, your favorite Banach space, separable Banach space, are even non-separable Banach space. So, using an algebraic isomorphism, but then you could transfer your favorite norm to R as a not only quasinor, but a norm which is discontinuous, non-measurable, etc. But we are not interested in pathologies, but in understanding things. Okay, the quasinormal groups come with their homomorphisms, which are bounded homomorphisms. The definition is exactly the same as the usual definition for linear operators. You need two groups, each with its quasinor, and then a bounded homomorphism from G to H is just an additive map satisfying an estimate of this type. And then the last n you can put here is the quasinorm of the homomorphism. And if you take quasinormal groups and bounded homomorphism, you get a very nice category where you can perform many categorical constructions such as quotients, pullbacks, push-outs. You have exact sequence and so on. Okay, but the leading idea is to see some infinite dimensional object by means of small quasinorm groups. So what is the key point in doing this? Just taking functions, taking sequences, taking random variables, and so on. So assume you have a standard quasinorm on Euclidean space, and you have a measure, for instance, the Lebesgue measure on an interval on the real line, or a discrete measure, or counting measure on the integers. You may consider this space, which is a new quasinormal group, where you, with this quasinorm, you just have to take functions, compose with the quasinorm, and integrate. And this is the quasinorm of the function. Then, okay, we need some hypothesis on the quasinorm. For example, that it has star-like balls to get that this infinite dimensional object is a topological vector space. But just using the pointwise multiplication. Let us see some examples. Okay, if you take a power here, then the L1 group is the LP space, and the group quasi-norm is roughly equivalent to the usual LP norm. This is, you don't take the P root, so you get the norm to the power P. Okay. If you take Lebesgue measure on the unit interval and this quasi-norm is quite interesting because it's bounded. Okay, and then you take the L1 group, then this group is the famous space L0, which is the space of all random variables, and the quasi-norm is in fact the usual metric of this space, which corresponds to the topology of convergence in measure. More interesting for us is that if you take right quasi-norm on the plane, this is this quasi-norm, and you take sequences that is a discrete measure, then you get the Carlton-Peck space Z1. This space has not appeared before because Manuel was talking about the C2 space, but you can get the same just doing the following. You take here the rib norm, fix some P, replace gamma by gamma 2P, and then form the group of sequences. In particular, if you take P equal 2, then you get the genuine Carlton-Peck space. Of course, these linear topological spaces can be very nasty, and well, not so nasty because because in any case the L1 quasi-norm is in all cases an if norm in the sense of Banach books. But in any case, we need some criteria to study the usual properties of topological vector space, for instance, local boundedness, or more or less to be a quasi-Banach spaces, local convexity and local boundedness, to be a Banach space, and so on. But there are very simple criteria for doing this. For instance, the L1 group is locally bounded, that is a quasi-Banach space, if and only if the seed quasi-norm is shrinkable, which means that you can find homothesis of quasi-norm strictly less than 1. Of course, you are all thinking that homothesis of small reason are such that, but they aren't in general. For instance, if you take for this quasi-norm, all homotheses have quasi-norm 1. So you can, of course, you can shrink any ball, but you cannot shrink simultaneously all balls with a small homotopy. Moreover, for instance, if you want to get a Banach space here, I mean a topological vector space with an if norm which is locally bounded and locally convex, then you need a quasi-convex quasi-norm at the beginning. Okay, and quasi-convex means that you have the same inequality of convex functions, but with some constant put here. If m is one thing, the quasi-norm is convex. So, but quasi-convex functions in finite dimensional space are equivalent to two truly convex functions. So, at the end, we find in the intersection of L1 groups and Banach space are the Fenchel-Orlich space, which are a relatively famous class of Banach space. Okay, so in some cases you can get Banach spaces. So certainly you will prefer to handle a true norm, and so where is such a norm? Oh, okay, you can use the Luxembourg functional, which is this is the original quasi-norm on the L1 quasi-norm. You take this infimum, and the result is that you get a homogeneous convex functional which has exactly the same unit ball as as the non-homogeneous L1 norm. This is is standard in the study of Orlich space. So let me present an application of these ideas to complex interpolation theory, and the application is the description of the interpolation spaces of Fenchel-Orlich spaces. So let me present ideas from interpolation theory. We need some background. First, we have to move to complex scalars because complex interpolation theory works with analytic functions, and so we take only complex spaces, but finite dimensional complex space. You should think about finite dimensional objects. And we make an additional assumption that our quasi-norms are balanced. That means that they have star-like balls. Of course, this is different from in the real case than in the complex case. So let me recall what this means in the complex case. The quasi-norm of you take some point and some complex number of modulus less than 1, then this decreases, then the quasi-norm decreases. Of course, to have some examples, you can consider any of the previous examples and complexify it, just in the same way that one applies the usual Taylor complexification procedure for homogeneous norm on real space. Then the next ingredient we need is the unit strip, which is the unit strip in the complex plane. With the closure, and then the strip has two parts of the boundary, the left part and the right part. And so the union of both lines is the boundary, the wall boundary. Then we need a little bit stricter, so the setting is the following. We need two quasi-normed groups with quasi-norms and one complex Banach space containing both. So we need two continuous inclusions. We need not to be bounded because the quasi-norm of X could mix very badly with the norm of sigma, so we admit or merely continuous additive inclusions injective. Then we can consider the group as subgroups of the containing Banach space, sigma, and we say that X0, X1 is a couple, but the couple are the embeddings. In any case, if you are not familiar with complex interpolation, you may think that X0 is the complex Euclidean space of finite dimension with some quasi-norm, and the same for X1 with another quasi-norm, and sigma is again Euclidean space with the usual topology. Then we need to introduce a certain space of analytic functions, which is roughly the same as Manolo mentioned in the preceding talk. And we need continuous function on the closure of the strip into the ambient Banach space. Continuous and bounded up to the boundary with analytic restriction in the interior of the strip and satisfying two boundary conditions, namely that the function in each part of the boundary takes values in the corresponding space. This is nothing in the simple example in which you may think, if you want, that all the space are the complex plane. And the point is that on each border, the function has to be bounded with respect to the corresponding quasi-norm. Not in the sense of a bounded homomorphism, but in the sense of having a finite supremum. Okay? In the simplified version, you might think, okay, that everybody is Cn. And if we put here the subnorm, then this space is just the product of n copies of the strip algebra, which is the disk algebra, but for the strip. Okay, so it's the same kind of object. And then we equip this space of analytic function with the quasi-norm. Is the maximum of the quasi-norm in each boundary, and we call it the Calderon space associated to the couple. And well, this is really a quasi-norm. And this is the setting in which complex interpolation theory works. Let me present some one-dimensional example. Oh, I forgot that I should interpolate. Okay. Then, having this space in hand, then we do the usual procedures. So take functions in the space, we fix a parameter, some point here, and we evaluate all functions in Calderon space at the same point, theta. Then we obtain some points in the ambient space, and we put the quasi-norm, which is this quasi-norm. Okay, for the notation is more convenient perhaps to write this and not this and this and not this if there is another couple to work with, right? And of course the identification of the quotient of the interpolated quasi-norm can be seen as a problem in geometric function theory. What? Because what we do is the following. Imagine we work on CN, and we have two quasi-norms, and we want to know what is the interpolated quasi-norm. The point is the following. So let me fix some theta here. And a radius r. And assume this is the ball of this radius for the gamma 0, no? You have another, but so the problem is you have function in the strip algebra that map this border inside this ball, and this other border, half of the border in this other ball, and then you evaluate the function here, and you obtain here some point. And the information you get is that this point is in the ball of radius r of the interpolated quasi-norm. So you are asking, where are going to go my points by using analytic function? And this has sense even in dimension 1. So some samples, easy samples, are the following. If we interpolate the power norms, this is in the complex plane, or in the complex lane, you get another power norm, which is comme il faut. And this is, in fact, this can be seen, in fact, as an interpretation of the celebrated Hadamard three lines theorem, but still in dimension 1, you can interpolate Orlich functions, which Orlich functions are quasi-norms on the complex plane. And again, you get what is expected. That is that interpolating, well, strictly increasing Orlich functions that we see as quasi-norm, then we obtain a new Orlich function, which is given by this formula. and this fits very well with what is known about the interpolation of Orlich function space. Okay. This formula is true, it's very old, and in fact appears in Calderon's paper. But the point is that we have here a typical statement in ponematics, which is to interpolate Banach spaces. This is both spaces here are Banach spaces with homogeneous norm. You need only to interpolate a very, 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 very simple object in one dimension. The point is, and what happens in higher dimensions, the difference between dimension 1, that is Orlich function, and higher dimension, by finite dimension, is that you move from Orlich function to Young function. Well, what happened is the same, but not exactly the same. So let me explain. What? And the point is that we need to change our method of interpolation. We need a different method of interpolation, which is the same for Banach space, but not for quasi-norms. So what we need the notion of an harmonic measure, which is very easy to understand. The harmonic measure of a point or theta point relative to theta point is a measure, a Borel measure on the border of the strip that has this property. If you take a function in the strip algebra, that is a continuous bound function up to the boundary, which is analytic on the interior, then you can recover the value of f at theta just integrating all the boundary with respect to harmonic measure. We are not really interested in which one is harmonic measure, but only in its existence. Then we can take the same function space as before and put there a different quasi-norm, which is an integral norm. So we take the function, put the L1 norm with respect to harmonic measure and on the left border and the same of the right border, and then we sum and you obtain a different quasi-norm. There could be some problems because we don't know exactly if this is a quasi-norm or it could be degenerate, but in finite dimension, this has no importance, so let me skip this. No. Once we have re-quasi-normed this space, we project the quotient new quasi-norm to the interpolated space until we define another interpolated norm here, which is the same as before, but we replace the Calderon norm, the usual Calderon norm here, by the Daher quasi-norm. And to distinguish from the previous case, now we write here H1 to remember that we have that the new quasi-norm comes from a norm of Hardy type. And there is a very important feature of Daher versus Calderon norms is that for Banach of quasi-Banach space, they are the same. That is, in general, see, if you have a couple of homogeneous quasi-norms, you obtain the same interpolated quasi-norm from the Daher method as by the usual Calderon method. And this result is in the root of many important results in complex interpolation theory. Many applications. And the point is that, for instance, we can prove that this result holds for non-homogeneous quasi-norms if are, for instance, one-dimensional convex functions, but is false for arbitrary Orly functions. But the point is that what we need is to interpolate quasi-norms by Daher method instead of by Calderon method. If you interpolate in this way, then the result that we're looking for is true, that is, thank you, es luego. That is, this result is the same for Fenchel-Orly spaces if we interpolate the baby's quasi-norms with the appropriate method. And the point is that we can prove this identity, but we can also apply Calderon's result, because this space is exactly the same as if we remove the H1 method, because this agrees isometrically with the usual interpolation space. So the point is that interpolating Fenchel-Orly space, interpolation of Fenchel-Orly space can be done with the Young functions, which are highly non-homogeneous objects. And of course, we are very proud of this result this week because it is very difficult to interpolate object with doesn't have unconditional structure. Just for instance, by the way, all Rochever's spaces are objects of this type. For an appropriate quasi-norm, the Rn space is an L1 space of a non-homogeneous quasi-norm, a group quasi-norm on the Euclidean space of dimension n. So, in some sense, Rochever space, Pony space are two faces of the same coin. So, thank you for your attention and passion.
Other questions? More remarks? Comments? I have a question, but it's only understandable for those who have seen the interview of Rowan Atkinson to Elton John.
Yes.
Have you thought of changing the name, the bloody name of Ponimatica to Gnomica? Yeah. Well, about the Raspberry Spaces, yes, there is something inside that we don't understand yet, because when you try to understand the subspaces and the quotient, the natural ones appearing in the Raspberry Spaces,
Okay.
precisely appears
Of
something
course.
like this phenomenon that we don't understand. This phenomenon.
This-
You have subspaces of dimension 1, in some sense, of dimension 2, of
Yeah.
dimension 3.
Okay. Yes. You can do exactly the same for all Rochever space, because recall that this is a categorical session. So the point is that taking sequence, taking values, taking L1 is a phantom. So when you have you can extract the seeds, the n-dimensional seed pony space of all Rochever space just from this interpolation schema. That is, you put here the power P norm, the power Q norm, and then take function on the strip of the strip algebra. Strip algebra is just this. This is the algebra with the sub norm, but with that different quasi norm. Then do you want your Hilbert space? Okay. Take values of the function, and then L1. Do you want Carlton-Peck space? Take functions and derivatives. Reserve and take L1. All exact sequence that have Rochever space are the same here, and you obtain them, and you obtain your usual Carlton-Peck sequence, Rochever sequence, and then swinging diagram, just written in 1, 2, 3 dimensions and taking sequence. And in fact, you can see the natural subspace taking subgroups.
I'll think about it. Any more questions?
Of course, what you don't have is the wonderful word or the jumping ham arguments, because you have fixed coordinates, so you can jump anything.
Okay, then 5 minutes, we'll be back. Let's stand it. we start? It's a great pleasure to introduce to you to Tommaso Russo, who will give us a smooth and complete talk about, oh well, smoothness and completeness.
Or maybe not complete. Thank you very much, Jesus, for the introduction, and thank to the organizers for organizing this event here. It's my first time here in Banach, and I'm very happy to be here. And thank you for inviting me. It's a great honor for me to have been invited by one of my favorite speakers in conferences in general, so I'm very pleased to be here. And one thing that I'm also happy about is not to be in the first day, so that yesterday I had the chance to learn that from Miguel, that here the talk should proceed at Banach speed. So yesterday evening I had time to cut out my slides from 50 to 10. So I'll have to go slow. So I'm going to talk about smoothness and completeness, but actually somehow these two things are, I will try to explain that these two things are opposite to one another. So if you have one, you probably don't want to have the other, and so on. This is one topic that I've been presenting at several conferences, me and also Sheldon, who's one of the co-authors of this research. But somehow, having been invited in the smoothness and in the renorming and geometric method sections, I really thought this was the most indicated topic I could present. And in my understanding, geometric methods means really that I should be drawing pictures, so I erase the board and I'm going to use all of it in the course of the lecture. So before I start, I want to advertise another conference that we are organizing in Innsbruck, in Austria, in September. It's 4 days long, but this is only the day where people are expected to arrive. We start on Wednesday 25th and we finish on Friday 27th. Here are our main speakers, and if you are, I mean, some of you got an email from us about the conference. Somebody was just received some message from me and so on. If you are in neither of the two lists and you want to know something, here is the webpage of the conference, and you can email us, three organizers, to ask anything, or you can just ask me as long as we are here in the same event. Okay, let's get started, and this is the first slide. It's only about what the setting is about. So here I'm only stating the main question that I will be considering in the talk. So the question is, if I have a Banach space, can I find a norm on the Banach space which is differentiable in some sense on a large set? And again, large has to be explained what it means. And there might be, of course, several different ways in which I can give a meaning to the word large here. So here are a few options that have been considered as possible notions of being large. In the volume that you probably all know by Benjamin and Lindenstrauss, there are this couple of problems. No, I'm already making a mess. This one. There are these couple of problems. I think they are in the notes and comments to chapter 4, I think. This is really a quotation from the book. If you have a smooth norm on some large subset of the space, can you obtain that space is Asplund? So can you say something on the space? Now, maybe you don't know what Asplund means. It doesn't matter. It just means if you have a norm which is smooth, then can you say something? Can you imply something out of it? And an explicit example that they have is, can you build a norm on L1 which is differentiable outside a countable union of hyperplanes? So you remove countable in hyperplanes, and outside there, the norm is differentiable. And to the best of my knowledge, this has been open since the book has been published, so 20 years ago. Something similar, in the similar spirit, in another book by Guerrero, Montesinos, and Zisler, asks whether if you take the space in L1 gamma, if you take the vectors that are finitely supported, so the linear span of the basis, can you build a differentiable norm on this linear span? This linear span is dense because everything is countably supported and is a convergent series, so the finite vectors approximate it. But can you build a differentiable norm on this subspace? And of course, maybe to you it's not obvious why you cannot do it in the whole space, but I'm going to explain. So for now, I'm just stating things. I'm not expecting that you understand them. It's just a list of questions. One more question that I attribute to Godfrey because I heard it from him. I don't know where he took it from. I probably should have asked him, but now it's too late. I will just quote it to him. If you have a norm which has a point of differentiability on every subspace, so you have your space, you cut with a subspace, and you have some point of differentiability there. Then you cut again, and you have some point somewhere else, and so on. Can you deduce that the space is Asplund? So somehow you have differentiability more or less in many points. Can you get something? For us, I will give only one meaning to the word large here. And large will mean containing a dense subspace. And you see that here the color changed. Olive means important. Text in olive is somehow the most important part of the text, right? So if I'm writing something in olive, it means that it's the most important part of the slide. So you can forget everything else and just remember that for the rest of the talk, you are looking at a dense subspace. So I would reformulate the question, which has been stated in this form for the first time by Sheldon, Peter, and myself in this 2020 paper. If you have a Banach space, can you find a dense subspace which admits a differentiable norm? So this is the only thing that I will be looking for in all the talk. Now, before I proceed in any detail, let me give a couple of references. There are 3 books that have been appearing. This is just chronological order. And you can see that this is the oldest also because they didn't find any decent photo of the first page. This is the best I could find on Google. It's kind of embarrassing, but I think it would have been worse not to put it. OK, now let's start from the basics. So I didn't define anything. I probably will not define almost anything, but at least let's try to motivate a little bit the definition. So let's really go from the basics on smoothness. So I would like to define a renorming theory as you have a Banach space. You want to find another norm where a certain property is achieved in the strongest possible ways, or is not achieved in the strongest possible way. For example, yesterday Jacopo was trying to give norms that are strictly convex but fail LUR property as much as possible. So they are strictly convex but completely not LUR, or some other things. And for us today, the property that we want is differentiability. So we want norms that are as differentiable as possible. OK, maybe what does differentiable mean? I'm not using the same notion that Jacopo used yesterday, the Gateau notion. This really is what is usually called Frechet differentiability, which just means that you have a tangent hyperplane at the point. So the function can be locally written as constant plus a linear term plus higher order errors. So there really is a tangent hyperplane, which is, of course, a bounded linear function. This notion is kind of rigid and stable. It does give you, of course, the same notion as in finite dimensions. And you have the usual definitions of smoothness. What does it mean that the function is C1? Well, the derivative is continuous. So the map sending x to the derivative is a continuous function. And what does it mean C2? Well, if you take this function, x goes to f prime. It's a function. You can differentiate it again, and so on and so on. You have the rules of calculus, so the derivative of the sum, you have the chain rule, all this. I mean, whenever you have a formula, the formula is proved in the same way for the finite dimensional and for the infinite dimensional case. Nothing changes. But for example, the chain rule fails for Gateau smoothness. It only works for this notion. You really need to have a pure linear approximation. And also implicit function theorem extends. It's not such a deep thing, so it does work as well. So this is the analytic point of view. There is a maybe dual perspective in the geometric sense. If you draw on the plane anything that looks like a differentiable thing without corners, then there is a lemma telling you that the norm is actually differentiable. So if there is no corner, the norm is differentiable as it should be. And maybe you're not surprised to hear that the proof uses the implicit function theorem. After all, I'm drawing some level set which is differentiable. You want to say that the function is differentiable. It has to be implicit function plus, of course, Minkowski functional. But it's not completely straightforward. I think it's one page in this book here. I mean, it is known from way before, but in this book it's proven in full detail in this one page or something. But I mean, it's standard and there's some technicalities. Okay, let's look at some examples. If I take the L1 norm in the plane, it's a square, so there is a corner, so it's not differentiable by the lemma. Okay, let's be a bit more ambitious and let's look at all LP spaces, not just L1. If P is even, the norm is C infinity. Why? Well, if you think at the formula of the norm, there is an absolute value because P is even, so you don't need the absolute value. So, I mean, you're taking a power and it's a differentiable function, so it should be no problem, and it is not a problem. If it's odd, well, there is an absolute value, and you have to remember how many times you can differentiate x to the 27. You cannot differentiate it 27 times, but you can 26. So you get exactly p minus 1 smoothness. If it's not an integer number, I should not move. If it's not integer, you can differentiate as many integer times before the value p. Short way to remember it, exactly the same differentiability as the function t to the p. So the differentiability in dimension 1 and infinity is the same. Again, it's a formula. It's calculus. It has to be the same way. The same way for C0, this new phenomenon. The same way for C0, no. Okay. For C0, the ball is a square. There is a corner. It's not differentiable. Okay, but this is not renorming theory. I mean, this is taking one norm and talking about that norm. So what I want to do in renorming theory is, can I find some norm which is differentiable? Maybe the canonical norm is not differentiable because it has corners. I'm not lucky, but if I change the norm, I can just kick out the corners. So let's try to do this. And in this slide, there is one part which is in olive, which is here. So somehow you can ignore everything that I say here and then only read the olive part below. Everything that I'm saying here is something that I recycled since my first talk in 2017. It was in Besançon. Somebody from the audience was here. Hopefully you don't remember. Probably you don't remember. I mean, the slide is essentially the same, but I'm changing a little bit. So the first thing is, if you have a separable, of course, I'm making such a mess with the pointer. Okay, if you have a separable Banach space with a differentiable norm, then the dual is separable. So for instance, in L1, you cannot have C1 norms. So the canonical norm is already the best one. You cannot get any smoothness if you just change the norm. It's not going to work out. And in little LP, it's the same. Now, I wrote it in this way, but what I really wanted to write is that the canonical norm of little LP has the optimal smoothness. If you're a norm, you are not going to get any better. But I'm not saying anything about C0 here, right? C0, I didn't say whether there is a norm which is differentiable or not. I will say it later, but not now. Then there is this funny theorem that if you have twice differentiability, both in the space and in the dual, well, you have to buy a Hilbert space. This is extremely strong as a result somehow. You really cannot have differentiability in the dual and in the space if you are not in a Hilbert space. It's extremely strong. And then another result, which again is mind-blowing by how strong it is by Robert Deville. If you have C infinity smoothness, there are two cases. You either contain C0, or you have to be super reflexive, fair, and you must contain LP for a P which is an even integer. So you cannot contain L27. It has to be 28. And now again, I'm talking about this C0 guy, but can I get the first case? So can I have C0 in a space which is very smooth? So can I have a C infinity norm on C0? Again, the canonical norm is a square, so it is not differentiable. Can I get something better if I renorm it? Can I get differentiable norms on C0? As I said, this is going to be explained later. There is this more result, which is here for two reasons. The first one is that I needed to fill the slide. And the second one is that there is this notion of LFC, which I'm not defining now, but I will define it later. So I'm just letting the shorthand slide in the slide for now. It doesn't matter. I will mention it later on. It's not important for now. So now the olive part comes. So the real content of this slide is smoothness does not come for free. If you want to have smoothness, you have to pay a price. In some cases, you have to pay a Hilbert space. In some cases, you have to pay some other price. But you cannot hope to have smoothness in general. If you take a Banach space, there is no smoothness. You have to have some assumptions on it. Now, all the proofs of these results use completeness. And now where completeness enters my talk. If you check all the proofs, they essentially all depend on some variational principles. It can be any equivalent variational principle or some smooth variational principle, compact variational principle, whatever. And variational principle use compactness. Completeness. So the proofs use completeness. Okay. Here I'm just copy pasting. So the important part that smoothness implies things, and that the proofs use completeness. But now, is completeness really in the matter, or is it just something that is convenient to have? So can I prove the things without having completeness? Maybe it's just a matter that people were assuming completeness because nobody really cares about non-complete things, or maybe completeness is really essential. So do the results require completeness? So one thing is proving it via completeness, and one thing is really completeness being essential. And for example, one might think, okay, look, if you're not complete, you take your norm space, you have your differentiability assumption, and then you take the completion, and you do something in the completion, and you prove something on the completion. So completeness is not really important. It's just a matter of simplifying your life. Or maybe not. Maybe completeness is really in the main matter. So let's take something which is not complete. I was really tempted to write completely incomplete, but this would have been kind of stupid to do. Take something which has a countable algebraic basis. I don't know, take the linear span of the polynomials on the continuous functions, take the C00, take whatever you like. And here there are some classical results coming from Canada. Both Van der Werf and Hayek were in Canada at these times. They were PhD students of Václav Zizler. So first, Van der Werf was able to build a norm which is differentiable once. On this, like take for example C00. This is more than enough to have an idea of what is happening. If you are in C00 or maybe L1, the finitely supported vectors in L1, you can have a C1 norm. And then Peter was able to get a C infinity norm, so pushing from 1 to infinity. And then later, together with Sheldon and Peter, we obtained an analytic norm. Now, I will say what analytic means, and it's just below here. But before I say it, let me point out one consequence of this, which is in olive, as you see. The consequence is if you're in a separable space, you can always find a dense subspace with a differentiable norm, where differentiable here is even analytic because it comes out of this. But if you don't like analytic, just take this one and get C infinity. So the problem I started with has a positive answer, which is this olive part, for the separable case. But still, it's 4 years ago, at least if you like analytic norms. Now, maybe what does analytic mean? Because Gilles used analytic in a different context. Analytic here means locally power series, like in complex analysis. Like I can expand it locally. And of course, this implies C infinity. Again, in finite dimensions, we all know it. In infinite dimensions, it's calculus, so it works the same. And I said that this is a consequence of this. How is it a consequence? Well, you take, this guy is separable, so you take a dense sequence. You take the linear span. It has a countable algebraic basis, so you can apply this result, and of course, you get this one. So this is really a direct consequence. And I think these two are actually equivalent. If you have some dense subspace, you actually can prove this stuff about countable algebraic basis. I think it is true, and I thought I did it before, and I was convinced. Now I don't want to say random thing, but it should be equivalent, but whatever. Now, when I'm in my affiliation in Innsbruck, we have this monthly seminar, and one of the speakers that I appreciated the most at some point said, you know, giving a 1-hour talk has one good side and one negative side. The negative side is that people will understand only one thing. The good side is that you can choose which one. So this is my pick. So if you want to understand one slide, I recommend this one. So what am I doing here? I'm saying that in C0, you do have a differentiable norm, which might not be obvious at first sight. I mentioned it twice already, so now I gave the answer. And then the second claim here is this result by Hayek. And I would like to explain why this is true, and somehow I would like to argue that this result is the secret of smoothness. Somehow the proof of this is how everything in smoothness works. This is the simplest possible case. So I would like to explain, as I said, geometric methods means that I should go here and draw stuff. So how do I do it in the plane? Now I draw the unit ball in the plane. And of course, something which is not so hard to imagine is I want to do something. I want to draw some convex body which is differentiable and then use my lemma from before. If I draw something differentiable, the norm is differentiable. So I go here and I cut out the corners. And I'm done. Well, okay, this should be tangent. They should be tangent. Come on, okay. So now the guy inside is differentiable. By the lemma, everything works, and I have it. Okay, can you write down a formula instead of the picture, maybe? Because if I just draw the picture, this is trivial, and you don't see what is happening. So I will still do it in the plane. And to do it in the plane, I have to look at this function. This really is from the real line to the real line. It's a function that is 0 up to 1 minus epsilon. And then at the point 1, it goes up to 1. So it goes up very fast, and it's convex. It goes up this way. And here it does the same. So it's 0, and then it goes up in a differentiable way. And of course, you can build these things like convolution or whatever things you like. So you can build this function. And now in the plane, instead of looking at the maximum between x and y, the absolute values, I replace the set of all points such that x and y are both less than 1. I replace it with a set of points such that phi of x is at most, plus phi of y is at most 1. And I claim that this guy is a set in red inside over there. Why? Well, if y is less than epsilon in 1 minus epsilon, this guy is 0 because I don't see small pieces. Phi of y is inside here, so phi is 0. So this is phi of x less than 1. But phi of x less than 1 means x between minus 1 and 1, because I'm here. So if y is small, it means that I should be using the red. Y small means that I'm on this line. So the unit ball contains this piece, and also this piece. Same argument, switching x and y. Maybe I did them wrong. No, y is small. Yes, I didn't write. Same argument, I have this piece. Now I have to argue about the 4 curves. But again, this function is differentiable, implicit function, whatever. The boundary of this set is differentiable by whatever reason. So it must be inside the unit ball. It must contain the red segments. It must be differentiable. It cannot be anything else than these 4 curves. So this idea of taking this sum with the phi is a way to do something that if you are on the bottom of for Antonio over there, they are the same thing, right? Because I'm drawing very close. So it's a maximum, but it's differentiable. So instead of using the maximum, I use this sum with the phi's, and I obtain something which, when we were working together, we called C infinity maximum, right? So this trick works in the plane. But now this works in C0 as well, just because I draw what C0 looks like. So I draw a vector in C0. It has some coordinates. They can be 1, and then at some point it has to go to 0 because it's a sequence that goes to 0, right? So maybe at first the coordinates are 1, but after some point the coordinates go to 0. So there is what over there I'm calling strong maximum. Strong maximum means there is a finite set of numbers that are big and everything else is much, much smaller. And then if I take the maximum, these guys don't play any role. Like the maximum between 1 minus something and epsilon is 1 minus something. This is irrelevant. But now if you take some vector which is very close to our vector, this cannot change, right? Because now I have some approximation. So this is something nearby. And the jump remains. Like maybe the jump now is not this one. Maybe it's here, and maybe now it's here. But whatever, I still have the jump, right? So if I'm in C0, for every point there is a neighborhood such that the norm only depends on these finitely many coordinates. And now if I do the same, instead of taking this sum of 2, I take the sum of all of them, the sum over j, 1 to infinity of phi xj, well, this is a finite sum. Because at some point xj goes to 0, so this is 0, so I have a finite sum. And in a neighborhood, it's the same because of the picture. So this function is locally finite, and so it is differentiable because this guy is differentiable. Its level set is the red guy, so the unit ball is differentiable, so the norm is differentiable. So if you take the Minkowski functional of the level set where this guy is at most 1, you get a differentiable norm, which is C infinity, because this function is C infinity. So this is the magic, and this works. And if you read, I would argue, all higher order smoothness papers, somewhere you find this function. This is true for all papers that I co-authored and or read. And I mean, I'm not saying that this is all papers, but some. This is really the key tool in higher order smoothness. Now, this proves in the sense, in the geometric sense, namely, I give a picture and I claim that this is the proof, the first line for C0. And now I would like to go to the second line, this countable dimension, and I will prove it through the method that we have with Sheldon and Petrin in our paper, which proves something more general about this weird guy, which is the linear span of the characteristic functions in L infinity. So how does a vector over there look like? Well, it is a simple function in the sense that it has finitely many values, so it is something like this. At first, there's some value, maybe it has something bigger, then it goes to some third value, but then it has to repeat the same values. So it cannot oscillate too much. Finitely many values. And now I do some trick, which Carlo used already, and this is, in polyhedrality, this is called Fomf trick. I scale the coordinates. I increase the first one by some number, the second one by something smaller, and I scale them up. So if you take this picture and I scale, this becomes something like this. Wait, this is not a function. I'm doing something. Sorry. And now, well, here there is a coordinate. Here there is the next one. I have a jump. I said that if I have a jump, I have smoothness and so on, right? So I look at the other picture, and the other picture tells me that it must work, and it does. So they really work the same way. Of course, then it took us, again, some calculations, but the picture tells you that it must work. You have to just set up the parameters in the formulas to make it work, and it does. Now, how do I get the countable dimension out of this? This is completely standard. Your space of countable dimension is a subspace of L infinity because L infinity is huge, it's universal, it's whatever. So you write it as the linear span of some sequence. This guy is dense, quite clearly. So I can approximate my vector Ej with something which has finitely many values, like this. And now, well, the linear span of Vj's is going to be the same. It's going to be isomorphic to the span of the Ej's. They're very close. I approximate them very well, so I get some isomorphism, and then this works. Maybe I have to use that Ej's are chosen to be an M basis, maybe not. If they are an M basis, the calculations are easier. But somehow I'm really saying that if I take one subspace, another one which is very close, they're isomorphic, and everything works. So this is the picture, and this is what we get out of it somehow. And this was the result that we had for let's say, separable or a bit more than separable things. Half of the time, amazing. I will be faster than that. For non-separable spaces, we had a second paper published a year ago. I mean, we started it during some waves of COVID, but we finished it during some other waves, and then it got published a year ago. And here, the assumption is that we have a fundamental orthogonal system. If you don't know what this means, read whatever property you like with a red pony, whatever, okay? Doesn't have to be anything. I will mention something on it, but whatever. It's a property. I take one certain subspace, which is dense. This guy is dense by this word, whatever it means. Now, in this subspace, I can do whatever about smoothness I would like to do. I have a norm which is C infinity, and simultaneously LFC. Again, this shorthand, now I will define it. I have a norm which is polyhedral and LFC. Polyhedral norms were mentioned already at least twice by Carlo and more times. And Alberto will also mention them again. So, I mean, it means that the finite dimensional sections are polygons or polyhedrons. So you have square-ish like norms. You have differentiable ones. And you also have norms that are simultaneously differentiable and LUR. Moreover, any norm on the space can be approximated by any of those three things. And also, you can even build partitions of unity. And as in finite dimensions, if you have partitions of unity, you can approximate continuous functions by differentiable ones. This is, again, pretty standard. So somehow, you can do everything that you like to do about smoothness. You have differentiability of norms, you have partitions of unity, you can approximate, and whatever works. There are a couple of things where you might say, maybe I can get something better here and here, and I will explain it in the next slide. So let me wait for a second on this, because I have to give this definition of LFC at some point. And here it is. Now, this is one of these definitions that people don't understand once they read it once. So there is a picture here waiting to be, actually the picture is there already. LFC means if you take a point, in some neighborhood, the norm has this form. It is a function of finitely many numbers. So somehow, locally, the norm is finite dimensional. LFC means locally dependent on finitely many coordinates. So locally, finite things. Why did I say that the picture appeared already? Well, the C0 norm is LFC. In a neighborhood, the maximum is only computed in these finitely many numbers. So it is what is written over there. So LFC, forget the definition, is this picture again. Okay? LFC means in a neighborhood you have finitely many numbers, whatever way you want to write it. And the example, I said it already, and I did not erase my picture, is this one. This is the way to remember it. Okay, I said this is the best thing you can do. But there are two ways where you might say, okay, no, you can do better. Come on, you might hope to do better. One is here. I was talking about analytic norms first. Why can't I get analytic norms? Well, analytic plus LFC is impossible. But why cannot I get analytic in general? And here there is a 1. I think everybody knows a number bigger than 1, right? So can't I get C2 plus LUR? Right? I mean, it's just a matter that 2 is bigger than 1. You don't have to understand much of what I'm saying. Now, in the next slide, I'm saying that this is not possible. And I did something stupid here because there is something in between that I don't want to say in between. So the first one is I cannot get analytic norms. C infinity is the maximum possible. In C0 gamma, no dense subspace has an analytic norm. So you can already take C0 to get something that doesn't have analytic norms. This was proved by Pełczyński for the space C0 gamma, and we adapted the proof. Doesn't change very much. It's almost his argument for the dense subspaces. Now there is this sentence that I want to say after, and here is the C2 LUR. If the norm is C2 plus LUR, then the space is superreflexive. The completion is superreflexive. So again, for C0 gamma, no dense subspace has a norm which is C2 LUR simultaneously. And the point is that if you have a norm which is C2 and LUR, you have one which is C1, and the derivative is uniformly continuous. And this is uniform smoothness. So you cannot have C2. So here, it's really, 1 is really the best you can do. Now, this hidden part, these analytics things. Here comes a problem that I really like, because by the theorem before, in L1, we can find a dense subspace with a differentiable norm, C infinity. It was actually proved before in this paper, but it's also a consequence of what we said now. But in the previous paper, we also have an analytic norm, provided that the cardinality of gamma is at most continuum. So if the space is not too large, we even get analytic. And I really believe that you cannot get analytic if you go after continuum, because somehow analytic is a power series. The power series is a series, so it is something countable. And this guy is a subspace of L infinity, so there is some separability in V star, whatever thing. This guy not. So somehow there has to be a difference. So I really expect that you cannot get analytic norms after this. But we don't know how to do it. So maybe you might like to try it. And now there was this Y. I was using one subspace. Maybe you don't like it. I mean, if you give me some subspace, what can I do? If it is my subspace, I'm happy. If not, I can just go behind the blackboard and cry, right? There is nothing I can do. So we were thinking for a long time what we can do to different subspaces. And here there are two answers in two different papers. I will not say anything more than one line each, well, 3 lines in total. One might say, okay, look, I mean, they're both dense subspaces. They can't be too different, right? They have to be very close. This seems natural. It's completely false. It's hopelessly false. In what sense it is hopelessly false is explained in this paper with Peter and myself, again from the same year of the other one. I mean, I'm not saying it here. I mean, after all, I should convince you to read the papers, right? So if I say everything here, you will not go to read the papers. So it's explained in that paper here. And in a recent work with also with Sheldon, which appeared online a year ago and is still waiting to be in some volume, but it's online already. In some particular cases, we do obtain results also in some other subspaces. In the sequence spaces, LP gamma, we do have it for some other subspaces. But again, there are some natural subspaces, but whatever. I don't want to give the details. So I'm just saying that there is some work going on some other subspaces. And again, something in olive. The main problem for us is if you can destroy smoothness completely. Can you find a Banach space where no dense subspace has a differentiable norm? You give me a Banach space, and whichever subspace I try to construct, there is no differentiability. I think Peter has been working on this problem since we started this project. We failed miserably multiple times. We still believe it would be very nice to have a result and an answer. There has to be some combinatorics behind, because if you have some geometric assumptions, we can do it. So there has to be some combinatorics to handle all the subspaces, but we just don't know which is the right combinatorial tool that we have to employ somehow. I mean, we have some attempts, but they all were all stuck at some point. Now, I said about this notion, maybe to justify the result, I should say something about whether this assumption is satisfied somewhere or not. So are there spaces which have this fundamental biorthogonal system? Here is the definition. It means it's biorthogonal, so the functionals are 1, 0, or the vectors. And fundamentals means that the vectors span something linearly dense. Now, which spaces have such systems? Here there is a short answer in olive, many. And now you might be happy with my answer and not want to listen to the rest of the slide, or want me to convince you that there are many. Now here is a list of things. I'm not giving any definitions. If you know what they are, fine. If not, just keep with the olive line. For example, Plichko spaces. Plichko spaces include all separable, I forgot to write it, but also separable are here. Weakly compactly generated, reflexive, C0 gamma, L1 for any measure, C of K for Valdivia or for compact abelian, and more. Calenda proved it recently that if you have a projectional skeleton, you also have a fundamental orthogonal system. And again, this includes duals to Asplund spaces, some pre-duals to von Neumann algebras, or JBW star tripods. I have no idea what this really means. I just copied from some papers. So I mean, you don't have to know it either. It's some spaces. Some more explicit examples, continuous functions on trees with the coarse wedge topology, L infinity gamma, or the countably supported versions if the index set is not too large. Spaces with quotients that are WCG and have the same density. So if you quotient onto a WCG which is as big as what you started with, you also have it. And here comes the most claim. If you assume Martin is maximum, this is true for all spaces of density omega 1. This is a beautiful result by Todorchevich. So, I mean, it's a list. There are more, and we mention all of them in our paper and with the references and so on. So if you know what this list means, fine. If not, stop here, and that's enough. OK, I still have a little bit of time. I want to explain very vaguely what is something behind the proof. These really are, maybe Sheldon remembers them, these really are the pictures that we were drawing when we were working on it. It was during the pandemic, so this is a screenshot from my tablet. And I mean, I'm not as good as Andres with drawing pictures on PDFs, so I've been very, very lazy and just took it from my tablet. So what is happening? First of all, our space Y has an LUR norm. This is Trojansky's renorming theorem. Or maybe it's hidden in the proof. It's not explicitly Trojansky, but implicitly. So the unit ball of a two-dimensional subspace, well, the unit ball in general is LUR. So it looks like a very round potato. Now my argument really is finite dimensional and in dimension 2. So I have my potato or orange, maybe it's better. I start in dimension 1. I have this direction, E alpha. I have the other direction, E beta. It's LUR, so I have slices that are small. I start cutting out slices around the points of the basis. So I cut out a piece of my orange here. I cut out another piece here. One piece here. One piece here. It's very not symmetric, but whatever. And I do it for every one-dimensional subspace given by the basis. So here is the same picture. I'm just changing the colors. In particular, in dimension 3, I get something of this type. I have my three-dimensional orange, and I cut out six slices, 2 per dimension. And now I iterate. In dimension 2, I want to cut out what I did not cut yet. I want to completely peel the orange without destroying what I removed already, because I did it already. So I start doing something like this. I take one point here, and I did not cut anything here already, so I do remove a slice, which is much, much smaller than the slice before. So I do erase stuff, cutting out slices here and here as well. And so on here, and so on here. And this is the, like this green slices here that, as you can see, these are the two-dimensional ones that are much smaller than the one-dimensional ones. So now I have this thin layer around the equator in which my orange has been peeled out, so it's not orange anymore, it's white. And then I do it in all the two-dimensional spaces, so I do it here as well. And I do it in the third two-dimensional one, which is, oh, it's so complicated with the right hand. I do it on these two-dimensional subspace and so on. And then I do it on the three-dimensional subspaces and so on and so on. What is the problem? The problem is that maybe when I take a slice out of this point, I destroy what's happening here. Because maybe this slice is very close to this subspace. So my idea would be that on the two-dimensional subspace, only those slices play some role, which means that I have polyhedrality because I have finitely many by compactness, right? So here, if at the end I only have those slices in the subspace, I have polyhedrality. So I have to avoid that this red guy, the bad guy, enters my other subspace and destroys the game. This looks easy because in the picture, this guy is far away from this guy. In order to actually get it to work, it took us one claim which is that nice. This is how you have to implement it somehow. And it was actually pretty technical. It took us a while to get the right condition. I mean, the proof of the claim is straightforward. It's pure induction. But understanding that this claim is the right condition to do all the procedure took us some amount of work. I really don't want you to digest the claim now. I think we all want to digest something else. So this is really not to be read. And I think it's a perfect moment to mention the references that that have been mentioned, that I've been quoting. This is the first paper from 2020 where we state the problem and have this essentially severable things. This is the dense subspaces are different. This is the fundamental stuff with the orange. It's orange. And then this is the last one about LP gamma and so on. And I think that's it. Thank you very much.
Do we have comments, questions, or remarks?
Thank you for your nice talk. Can you tell me, so the differentiability is with respect to the subspace, so that means in the directions of the subspace, right?
Yes.
Could it be extended or strengthened to have differentiability in the directions of the whole space?
Yes, actually, yes. I did not say it, but you are absolutely right. Good point. It is because of LFC. This formula is stored in Y, but the functions are defined everywhere, and G is defined everywhere. So this guy is differentiable because G is differentiable. I mean, when you build it, G is differentiable. Because if you want this to be differentiable, you will build G to be differentiable. And this is defined everywhere, because the functionals extend to the completion. So if you have LFC, for free, you get differentiability everywhere. So actually, you have a norm which is differentiable at all points of Y. And even more, because this is LFC, so this works in a neighborhood. So the norm is differentiable on an open set containing this dense subspace. So it is even stronger. But this comes as a byproduct of LFC. And it does not come automatically for free from the other paper. It's really hidden in this equation here.
Any other question?
So sometimes these C1 and LUR norms, well, in the usual context, come from Asplund averaging. Does this happen sometimes in your?
No, it actually comes from your technique, from your paper. Because, I mean, yeah, maybe I should have said it, sorry. There are some results where you have C1 and LUR simultaneously. It's done in separable spaces. It's done in C0 gamma into distinct vectors, and then it's done by Petra and Tony in continuous functions on omega 1, and if you have a PRI with some properties. And their result is extremely technical, and our proof here is essentially the same argument that you have, just adapted accordingly, because instead of the projections, you use the one-dimensional projections. You are in the linear span, so you don't have to approximate, and it works. Essentially, it's a variant of your argument. So it's Trojansky's renorming, push, using your method. So this is really a consequence of what you did somehow.
Still one? Any other question, comment? Then let me indulge me to say a couple of things you mentioned about all the talks. Probably the first time I saw Tommaso was a conference in Bologna by the time you spoke Italian in Italian,
Yeah.
not now that he speaks English in German, he solved a problem I put with Piero Papini about the
that
constant that by then. And the second about the paper he mentioned, the Journal of Fashion Analysis, that's a wonderful paper, no matter how you look at it. The core of it is that we all know, all my students over there know, and they prove it, that all Hilbert spaces are isometric, depending only on the dimension, right? All Hilbert spaces are isometric. So you can say, well, pre-Hilbert spaces, I mean, dense subspaces are also equal, more or less. He should have entitled the paper, quoting the musical Chicago, equal my ass. Okay.
But very few referees would have accepted the title, and probably you would have been the only one.
Yeah. Anyway, let's thank the speaker again. We'll meet this evening at 4.
I have to get rid of stuff.
So I have a stupid question, so I didn't